Hello and welcome to our lesson on matrices and systems of equations. This is going to be from section 10.1 in our text. We have a lot of material to get through in this lesson, so let's get started. And the first question you may be asking yourself is, what is a matrix? Well, to answer that question, we're going to look at problem number 7 from the text. Okay, so here in problem number 7, you can see that we have a system of linear equations, two equations with two unknowns, and in order to convert that into a matrix, several things have to happen. First of all of the variables need to be on the left-hand side, and the constants need to be on the right-hand side. Next, the variables need to line up. So all of the x's lined up, all of the y's lined up. And it would be nice if the variables were in alphabetical order going from left to right, which they are. And then once those conditions have been satisfied, in order to write the matrix, you're just going to start with a pair of brackets. We are going to need a vertical bar that represents the equal signs. And then technically this is called an augmented matrix. The word augmented means separated. It's got a separator there separating the variables from the constants. And then each row of the matrix is going to correspond to an equation where we basically strip off the letters and have only the coefficients. So the first row of this matrix would be 2, -1, 7, -1 because the coefficient of y there is understood to be -1. And the second row of the matrix would be 1, 4, -5. And that is it as far as writing the matrix. If they ask you to write the augmented matrix for the system of linear equations, that's it. That's done. I think we should maybe look at one more example. Problem number 9 from our text is also a system of linear equations, but this time we have 3 equations with 3 unknowns. If they want us to write this system of linear equations as an augmented matrix, remember the first thing that you need to make sure of is that all of the variables are on the left-hand side and the constants are on the right-hand side. And next, you need to make sure that the letters are lined up, X, Y, and Z. And if those conditions are satisfied, then you can go ahead and write your augmented matrix. So here the first row is going to be 1, -2, 3, and 12. Our second row is going to be 2, 0, -4, 8. Notice that there is no y variable in the second equation, and so we have to input a 0 for a placeholder indicating that there are no y's there. And the third row in this system would be 0, 3, 1, 7. Again, there is no x, so we would put a 0 placeholder in the x column for that equation. And the coefficient of y and z, 3 and 1, and the constant. And so again, that is how you write your system of linear equations as an augmented matrix. Once you know how to write the matrix, then we can talk about our technique called Gaussian elimination that we're going to use to solve the system of linear equations. Now, if you think back to chapter 3, we've already covered 3 techniques for solving a system of linear equations. We talked about how to solve by graphing, the addition method, and the substitution method. So with this section, we're going to add another weapon to our arsenal for solving systems of linear equations, and that's Gaussian elimination. Now that process involves using row operations to get to row echelon form so we can use back substitution to find the solution. So again, like I said, once you know how to get the matrix, the next thing we need to talk about is, what is a row operation? Well, there are three types of row operations. There is a row swap, row multiplication, and then row multiplication with addition. And we will demonstrate all of those within the examples that we're going to look at. The purpose of knowing and using row operations is to get to row echelon form. So down here, I've written examples of row echelon form. What I need you to notice is that these are both matrices. The first one would be for an x comma y, a system of two equations with two unknowns. The other matrix is for the x, y, z, a system of three equations and three unknowns. And the characteristics of row echelon form, there has to be ones on the diagonal, and everything below the diagonal are zeros. So whether it's a system of two equations or a system of three equations, row echelon form again has ones on the diagonal. Everything below the diagonal is zeros. So if you look at our example number 7 over here, you can see that the diagonal does not have ones, and the number below the diagonal there is not 0, and that's what row operations will help us to get to. Row operations are what allow us to get the numbers to become what we need them to be. Once you get to row echelon form, then we're going to use back substitution, and that process will help us to find the solution. Now, before I go into an example, there is one other thing I need to mention, and that is that the book also refers to a process called Gauss-Jordan elimination. Now, how is Gauss-Jordan elimination different than Gaussian elimination? Well, Gauss-Jordan also uses row operations, but instead of getting to row echelon form, Gauss-Jordan is used to get to a form called reduced row echelon form. And what is different about reduced row echelon form, using a matrix that has 3 variables and 3 equations, reduced row echelon form, not only does it have ones on the diagonal, not only does it have zeros below the diagonal, but it also has zeros above the diagonal. And then over here you would have numbers like A, B, and C, some set of numbers. The advantage to Gauss-Jordan, the advantage to reduced row echelon form, is if you translate each row back into an equation, it actually gives you the solution. So remember that each one of these rows corresponds to a variable. So this would be the x, the y, and the z. And this first row, if you translate it back into an equation, it would say 1x, which is just x. There would be no y and no z. Remember, the vertical bar means equals, and you would have your solution for x. Translating the second row would give you the solution for y, because you would have no x and no z. You would have 1y equals b. And translating the last row back into an equation, you would have no x and no y. 1z, which is just z, equals c. So that is the advantage to Gauss-Jordan elimination, because if you can get to reduced row echelon form, you actually have your solution for x, y, and z. But to minimize the amount of row operations that we need to use, we're only going to use Gaussian elimination to get to row echelon form, and then we will use back substitution to find the solution. Okay, so that's where we're headed. Now we're going to look at some examples. Our first example, problem number 11, here they have given us an augmented matrix, and the instructions say write the system of equations that corresponds to the augmented matrix. Here they don't want me to solve, they just want me to translate this back into the system of equations. So the first row would correspond to our first equation, where we have our x, our y, and our constant. Translated back into an equation, that would be 3x minus 5y equals 1. And translating the second row back into an equation, you would have 1x, you don't have to write the 1, plus 4y equals -2, and we're done. That is all there is to converting from matrix into a system of linear equations. Next, number 14, we have the same set of instructions. Here they want us to write the system of linear equations that corresponds to the augmented matrix. And so in this case, since we have 3 rows, each one of these columns is going to correspond to a variable. We're going to need x, y, and z. And if you're wondering, do I have to use x, y, and z? The answer is no. You can use any variable you want, but you do need to follow the instructions. So if they specify the variables to use, you need to use those variables. So our first row would translate into -x minus 2y plus 3z equal to 6. Please be careful and get the signs correct. Next, notice that we have no x. So we're just going to say 4y plus z equals 2. And the last row has no z. So that will translate into 2x minus y equals 9. And again, that is the answer. That is all they want for this problem, is the system of linear equations. Our next example, problem number 16, here they have given us a system of linear equations, and the instructions say solve the system using Gaussian elimination or Gauss-Jordan elimination. And so we are going to use Gaussian elimination. I don't plan to ever demonstrate Gauss-Jordan because that's really more of a goal for a linear algebra course. We can get by in this course with only Gaussian elimination. So the first step in the process is to convert the system of equations into a matrix. So we're going to start with our brackets. We've got our vertical bar that represents the equal signs. The variables are lined up and on the left. So this is ready to be translated into a matrix. The first row would be 2, 1, and 1. And the second row would be 3, 2, -2. Once you have written the system as a matrix, then we can focus on using our row operations to get to row echelon form. So just to make a note here, our objective is going to be to get this number to become a 1, this number to become 0, and this number to become 1, because you need 1s on the diagonal, and everybody below the diagonal needs to become 0. Okay, so the order that you achieve those objectives is you start in the upper left-hand corner and you work your way down and over. So my first objective is to convert this 2 into a 1. I can do that through row multiplication. Okay, now check this out. I'm going to take 1/2 and multiply everybody in row 1 by 1/2, and that'll produce a new row 1. This is the way you write your row operations, okay? You're going to need to know this notation. Multiplying row 1 by a half in order to achieve, this means in order to get a new row 1. Now notice I did not mention or include row 2, so the very first thing I'm going to do is copy and paste the row that doesn't change. Row 2 is not going to be affected this time, but row 1 is going to change. If I multiply through by a half, half of 2 is 1, half of 1 is a half, and half of 1 is a half. And that is that row operation executed. And do you see that I achieved my objective of getting a 1 in the upper left-hand corner? Now my next objective is going to be to get this 3 to become a 0. To do that, we're going to use a row multiplication with addition. Okay, so check out how this works. The thought process is, what would cancel out positive 3? Well, negative 3 would. And what could I multiply this number by to get negative 3? Well, the answer is negative 3. So what I'm going to do is I'm going to multiply row 1 by negative 3 and then add to row 2 to get a new row 2. Okay, so one more time. Again, what's going to happen is we're going to take everybody in row 1 and multiply by negative 3. Whatever we get from that multiplication, we're going to add that to the corresponding element in row 2, and that will produce a new row 2. And now what I'm about to say is important. The row that you're adding to is the only one that changes. So in this row operation, row 1 is not going to change. And so what I can do is I can simply start my new matrix. I'm going to copy and paste row 1 because it's not going to change. And then we can execute the row operation to get our new row 2. Here we go. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. So I'm multiplying by negative 3 and then adding to the corresponding element to get my new row 2 element. All right, let's rinse and repeat. Negative 3 times a half. What is negative 3 times a half? Well, that's going to be negative 3 halves, which I then have to add to the corresponding element in row 2. So I'm going to have to add 2 to that, which means I'm going to need either a common denominator or a calculator. So if I use a common denominator, first I'm going to take that 2 and F it up, and then multiply top and bottom by 2, and that'll give me negative 3 halves plus 4 halves, which is 1 half. And that'll be the corresponding element in row 2. And if that was confusing, don't worry, we're about to pull a Britney Spears. Okay, hit me, baby, one more time. Negative 3 times a half, again, is negative 3 halves, which we then have to add to the corresponding element in row 2. So we're going to be adding negative 2. Again, I need a common denominator or a calculator. We're going to have negative 3 halves plus a negative really means minus 4 halves. Negative 3 minus 4 is negative 7 halves. And I apologize, that is really effed up, but you can't help it. It's really fractioned up, but sometimes you cannot avoid working with fractions. So that is it for executing that row operation. You can see I now have a brand new row 2. And if we take an inventory of where we're at, I now have a 1 and a 0, which I needed. Now my final goal is to get this 1/2 to become a 1. Once I get that to become a 1, then my diagonal would be all 1s, and everybody below that would be a 0, and that would mean that I have achieved row echelon form. Now, in order to get this to become a 1, I'm going to use a row multiplication. What would I multiply a half by to get 1? Well, the answer is 2. So I'm going to multiply this time row 2 by 2, and that's all I'm going to do to get a new row 2. Notice that row 1 is not mentioned this time, so row 1 is going to stay the same. So the first step would be to copy and paste the row that doesn't change. Row 1 is not going to change, so I can copy and paste, and then I can execute the row operation, multiplying everybody in row 2 by 2. So 2 times 0 is 0. 2 times a half is 1. 2 times negative 7 halves is negative 7. All right, so now if we take an inventory of where we're at, notice we have 1s on the diagonal. Everybody below that is 0, so now we have finally reached row echelon form. Now that we're in row echelon form, I can talk about back substitution. What is that? How does it work? Well, back substitution says that you start at the bottom and you translate back into an equation. So this would be our x and our y. Notice it says no x, 1y equals negative 7. And that would be our solution for y. Once we know y, we can get x by going back up a step, translating this back into an equation would give us x plus 1/2 y. But I already know what y is. Y is negative 7, so I can substitute for y equals 1/2, and then I can solve this equation for x. So that's going to give me x minus 7/2 equals 1/2. Then if I move that to the other side, it's going to make it plus 7/2, which I can then combine like terms. I already have a common denominator, so that would make that 8/2, which is 4. And so then that would tell me x is 4. Once I know x and y, I can write the solution to the system of equations as an ordered pair. Okay, so as an ordered pair, this solution would be 4, negative 7. Please make sure that you do put those numbers in the right order, and that's going to be the same order as your variables were in your equations. And that's it. That is using Gaussian elimination to solve a system of linear equations. And for our last example in this lesson, we're going to look at number 32. This is the culmination of all we've talked about in this lesson. Here we're going to solve the system of linear equations using Gaussian elimination. The first step is to convert the system into a matrix. So we start with a set of brackets. Remember, the vertical bar represents the equal signs. And then as long as the variables are lined up, x, y, and z, we can translate each equation into the corresponding row of the matrix. So our first row would be 2, negative 3, 2, and 2. Our next row would be 1, 4, negative 1, 9. And our last row would be negative 3, 1, negative 5, and 5. And let me pause just for a second to make sure you understand how important it is not only to copy these equations down correctly, but when you're writing your matrix, to make sure that you pay attention to detail. If you miss even one sign, it's going to result in instant death. So pay close attention to what you're doing. One little miscopy, one little error, and the whole thing is, well, screwed. The whole thing will be screwed. All right, so let's talk about strategy next. Remember, we're trying to get ones on the diagonal, and every element below the diagonal, every element in this little triangle needs to be 0. Since the middle row has a 1 as the x-coordinate, if I do a row swap, swapping rows 1 and 2, that will get a 1 in the upper left-hand corner, and then that objective will be achieved. Now, just like chess, it wouldn't hurt to think a couple of moves ahead. So once I get this 1 switched up here, once this element becomes a 1, the next 2 objectives will be to get these 2 numbers to become 0. That is our strategy to start with, is to get the first column the way it needs to look. And we do need to make sure that we use the correct notation and notate every row operation. So first, we're going to do a row swap. I'm going to swap rows 1 and 2. Notice row 3 is not going to change, so I'm going to start and copy and paste the row that doesn't change, and then we're going to execute our row operation. 1, 4, -1, 9. That is row 2. Becoming row 1, 2, -3, 2, and 2. Row 1 now becomes row 2. Again, our next 2 objectives are going to be to make the 2 and the -3 become 0. And to speed things along, I'm going to do both of those row operations in the same step. So in order to make this 2 become a 0, I'm going to need to use -2 multiplied by row 1. Okay, again, think about it. If I multiply 1 times -2, that'll make -2. And then if I add that to row 2, it'll make this element become 0. So we're going to take -2 times row 1 plus row 2 to produce a new row 2. We're also going to get -3 to become 0 by multiplying row 1 by +3, adding that to row 3 to produce a new row 3. If I multiply row 1 times 3, 3 times 1 is 3, added to row 3 will make that become a 0. And did I mention that you're going to have to not only know this notation, but know how to come up with these row operations on your own in order to achieve your objectives. The first thing I need to do is copy and paste the row that doesn't change. Here, row 1 stays the same. And then we're going to execute each row operation to get the new row. Starting with this row operation, we're going to multiply -2 times row 1, added to row 2 to get our new row 2. Okay, so here we go, multiplying row 1 by -2. -2 times 1 is -2. Added to 2 gives me a 0. Objective achieved. Next, 4 times -2 is -8. -8 plus 3 is -11. Next, -1 times -2 is +2. Added to 2 is 4. And last but not least, 9 times -2 is -18. Added to 2 is -16. And so there's this row operation executed correctly. Next row operation, 1 times 3 is 3. Added to -3 is 0. Next, 4 times 3 is 12. 12 plus 1 is 13. -1 times 3 is -3. -3 plus -5 is -8. And last but not least, 9 times 3 is 27. 27 plus 5, 32. All right, and now if we take an inventory of where we're at, the diagonal needs to be 1s. I've got the first element done. Everybody below that needs to be 0. I have 2 out of 3 done there. The next objective is now to work on column 2. I need to get this element to become 1 and then this element to become 0. Those are our next 2 objectives, starting with -11 becoming 1. I'm going to do that through row multiplication, multiplying row 2 by -1/11. Okay, now think about that. -11 divided by -11 would give me a 1. But in order to write it as multiplication, instead of dividing by -11, you would multiply by -1/11. And those 11s would cancel and give you +1. That will produce a new row 2, and that is the only row operation I'm going to do in this step. All right, here we go. Multiplying row 2 by -1/11. 0 times anything is still 0. So that retains the 0 that I got. -11 times -1/11. Negative times a negative makes a +1. -1/11 times 4. 4 could be expressed as 4/1 times -1/11 means that I'm going to have -4/11, and -16 can be expressed as -16/1 times -1/11 is going to give me, negative times a negative makes a +16/11, and that finishes the row operation. And unfortunately we ended up with fractions, and I apologize. You can't help it. Sometimes you end up with fractions involved, and that's okay. Now, our next objective, remember, is to make this 13 become a 0. And we're going to use row 2 to achieve that objective. So think, what would I multiply 1 by that would cancel out 13? And that answer is -13. So the next row operation is going to be -13 times row 2 added to row 3 to get a new row 3. We want this 13 to become a 0. The other 2 rows are going to be unaffected. So again, the first thing you want to do when writing this new matrix is copy and paste the rows that don't change. The first row and the second row are not going to change. So we're going to recopy them just the way they look. And then we're going to execute the row operation, multiplying every element in row 2 by -13. And then whatever we get from that, we're going to add to the corresponding element in row 3. All right, so to start it off with, that's going to be 0 times -13, which is 0. And then 0 added to 0 is still 0. It's important that you retain these objectives that we've already achieved. Next, 1 times -13 is -13 plus 13 is 0. Objective achieved. Next, -4/11 times -13. Now I'm going to write that like this. -13 is a fraction. If I multiply straight across, that's going to be, well, negative times a negative makes a positive. 4 times 13 is 52. 11 times 1 is 11, so that's going to give me 52/11. And then don't forget, after you multiply, you then have to add to the corresponding element in row 3. So we're going to need to add 52/11 to -8, which I'm going to make that a fraction, and we're going to need a common denominator. So we're going to multiply top and bottom by 11. That's going to give us 52/11 minus, because plus a negative makes a minus, 88/11. And then I simply need to know what is 52 minus 88. And that is negative 36/11. All right, and for the last element here, we're going to need to multiply negative 13 times 16/11, which I'm going to write as negative 13 over 1 times 16/11. And multiplying straight across, I'm going to need to know what 13 times 16 is, and that is negative 208 over 11. And then don't forget that we need to add to the corresponding element in row 3. So we're going to have to add that to 32, which I'm going to write as 32 over 1. And then I'm going to need a common denominator. So multiplying top and bottom by 11 is going to give me negative 208 over 11 plus whatever 32 times 11 is, and that is 352. And then I simply need to do negative 208 plus 352 to get that final piece of the puzzle, and that is 144. Now, if you're wondering how am I doing that arithmetic, I'm not doing it in my head. I'm pulling up my calculator, doing that arithmetic, and then writing it down. I'm just not showing the calculator button pushes. Now, if we take an inventory of where we're at, 1's on the diagonal, all but this guy. Everybody below the diagonal is zeros, so I only have one objective left to achieve, and that is I need to get this to become a positive 1. We can do that through row multiplication, multiplying through by the reciprocal. So if I simply multiply row 3 by negative 11/36, and that is going to produce a new row 3. And again, the first step in doing this row operation and writing the new matrix is to copy and paste the stuff that doesn't change. And then we can execute our row operation, multiplying every element in row 3 by negative 11/36. 0 times anything is still 0. So notice we get to retain the objectives that we've already achieved. Multiplying any fraction by its reciprocal will give us a 1. And a negative times a negative does make that a positive 1. And then the last thing we need to do is multiply negative 11/36 times 144 over 11. And we're going to simplify before we multiply. The 11s will cancel. And I need to know if 36 divides into 144 evenly. And it does. 36 goes into 144 4 times. Oh, and don't miss the sign. Negative times the positive makes that a negative. And that is it for the row operation. Now, if we take an inventory of where we're at, you're going to notice that we are now at row echelon form. The diagonal is all 1s. Everybody below the diagonal is a 0. And now we can use back substitution. So, using back substitution, we start at the bottom and work our way back up to the top, converting each row back into an equation. And remember, this is x, y, and z, so we have no x, no y. 1z equals negative 4, and that is our solution for z. Then we go back to the next row. We're going to convert that into an equation, and we're going to substitute for z as we go. So that's no x, that's 1y, minus 4/11 z, but z is negative 4, equals 16/11. And then we simply need to solve for y. So doing this multiplication, negative times a negative, that's going to make that a positive. 16/11 equals 16/11. And then if I move that to the other side, that's going to make that minus 16/11. Well, and look at that. Anything minus itself is 0. So that's going to tell us that y is 0. And then I'm going to go back up to the top. I'm going to translate that row back into an equation. And I'm going to substitute for y and z. That's going to give me x plus 4y, y is 0, minus z, z's negative 4, equals 9. 4 times 0 is 0, that's gone. Negative and a negative make a positive. Gives me x plus 4 equals 9. And moving the 4 to the other side gives me x is 9 minus 4, which is 5. And that is done. The only thing we need to do to finish that off is to write our solution as an ordered triple. So the solution to this system as an ordered triple would be 5, 0, negative 4. Okay, now as a bonus, what I would like to do is show you again how you can use the Casio ClassWiz to check this solution. It's not going to check your work, okay? The ClassWiz is not going to do these row operations for you and show the work, but it will verify this solution. The way we do that is we go to Menu, we're going to scroll down and over to the equation/function option, and we're going to choose simultaneous equation. The number of equations, or the number of unknowns this time, was 3. So we're going to click 3, and then you're simply going to fill in the coefficients for the first, second, and third equation. So starting at the top, we had 2, negative 3, 2, and 2 for the constant. And then the second equation, the coefficients were 1, 4, negative 1, and 9. And last equation, we had negative 3, 1, negative 5, and 5. And then if I hit equals one more time, it's going to give me the answer for x. Hit equals again, and again. It's going to give me the solution for x, y, and z. And if you click equals again, you're going to see that it cycles through. So x, y, and z, our solution is verified. And this Casio will also check your 2 equations with 2 unknowns as well. Oh, and if you need to get back to regular calculator mode, that would be Menu and 1. Takes you back to the regular calculator mode. And that's going to do it for this particular lesson. So if you have any questions or comments about anything that I've covered, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.